Discrete Math. We're going to start a new chapter, chapter 6. We're going to talk about sets. Objectives. Sets. Okay, perfect. Very well. So, talk about sets. Well, why sets are important for us, especially in computer science. Sets are the building blocks of structured query languages related to database. So, the fundamentals for database structured query language, the fundamentals are built upon sets. Very well. So what is a set? Remember, at the beginning of the course, we started talking about some basic elements in discrete math. One of them was set. So 6.1, page 1. Recall that a set is a collection of objects, of numbers, you name it, of objects, numbers, and so on. That's how we define sets in general. And we say that, hey, to denote sets, let us use capital letters like S, A, B, C, and the rest of it. We have different methods representing a set. We can either use roster method to list the elements of a set, or just set builder notation mentioning the properties of that set. So note that we either use roster method to write the elements of a set, or we use set builder notation. Set builder notation. Very well. After defining a set, remember that we're interested in forming some new sets. The easiest way to introduce a new set is to take the subsets, sub-collection of that set and say, hey, these are new sets. So recall that. Let A and B be two sets. We say that A is a subset of B if and only if, so we read it this way, A is a subset of B. This is the subset notation. If and only if for any element that you take from the set on the left, that random element lands in the second set on the right-hand side. For any x in A, x belongs to B. We can use Venn diagram to visualize this as well. Venn diagram says, hey, suppose you have set B. A is a subset of set B. So it means that set H is included in set B. If I take any random element in set A, that element is definitely in set B. Very well. So take a look at this example. Example. This example says, well, let A be a set including just one member. The cardinality of set A is 1. Set B is the set including 1 and a set including 1. Well, question says, is A a subset of B? Remember the definition of proper subset? Can we say that A is a proper subset of B? Well, the answer to the first part is yes, of course. If I take the element in set A, which is 1, I exactly see that element lands in the larger set B. So the answer here is yes. Is A a proper subset of B? You have different methods investigating to see if A is a subset of B or not. In this case, you can say that, hey, since set B has another element that is not in set A, it means that A is a proper subset of B. Proper subset of B. What's the meaning of that? It means that there is no way these two sets are equal to each other. So again, the answer here is yes as well. Since the answer that we can write, the justification that we can write is, since B has 2 elements and A has only 1 member. That's the justification behind it. Since the second set is larger than the first set, definitely there is no way they are equal to each other. So we have proper subset. So another example for you. Are these two sets equal to each other? Or which one are the subset of the other one? So we are working on subsets. Let's talk about equality later. So we are on page 2. Here we have this case. It says A is defined as the set of all integers like M, such that the condition that M is equal to 6R plus 12, and R is another integer. The second set is set B, which is defined as the set of all elements like N all integers like n such that n is equal to 3s. N is 3s. S is also an integer. Which one is true? A is a subset of B, or B is a subset of A. Which one is true? Very well. So let's take a look at these two sets. My first set is, okay. My first set says, hey, I have all of the integers that can be written as 6r plus 12. My second set is the set of all multiples of 3. Well, which set is bigger than the other one? Is it A included in B, or is it B included in A? Let's take a look at some of the elements in A, some of the elements in B. So A, B. If I plug in 0 here, I get 12. If I plug in, for example, -1 here, I get 6. If I plug in 1 here, I get 18. And I can continue this process. For this guy, if I plug in 0, I get 0. If I plug in 1 for S, I get 3. If I plug in -1 for S, I get -3. Well, okay. It seems like if I multiply 6 by 2, I get larger positive numbers. And at the same time, if I multiply, for example, if I multiply this guy by -2, I get 0. If I multiply by -3, I get -18 plus 12, which is -6. It seems like I don't get to 3 in the first set. Whatever I plug in, I get different numbers. This guy has 3 in it somewhere. Okay, listing it is not very efficient. That's why we don't like listing when we have sets with a lot of numbers, a lot of members in them. We just tried our best, to see what's going on in these two sets. So write down not efficient. So what I'm going to do, I'm going to take a random member, a random element, not just a specific number, any random generally taken from set A, and show that that element lands in B. If I'm successful in that process, then I proved A. If not, I try to take a random element in B and show that that element lands in A. If I'm successful, then it is true. Otherwise, there is no relation between these two sets. Okay, take a look at this. Here, I'm taking a random element for any M in set A. M is written as 6r plus 12. What I'm going to do, I'm going to factor out 3. If you factor out 3, what you get 2r plus 4, which can be written as 3 times s. So any elements in A, any random element in A can be written as a random element in B. This belongs to equals to n, belongs to B. So what's the meaning of that? It means that A is a subset of B. Okay. So far I know A is a subset of B. I'm happy about this result. But what about this guy? Can I show that B is a subset of A? It means that if I take a random element here, 3s, I should be able to write it down in this form, 6r plus 12. Okay. I'm going to give you a counter example here. Counter example. This is a general statement, and I would like to disprove this. Okay, what is your counter example? The counter example is using n equals to m, set it equals to 3. Let n be 3. If 3 is a member of A, then the counter example doesn't work. But if it's not a member of A, then you are done with your counter example. Take n to be 3. So if 3 belongs to set A, what's the meaning of that? It means that 3 can be written as 6r plus 12. But what's the meaning of this? It means that 6r is equal to negative 9. It means that r is equal to negative 3 halves. R is an integer. But this guy tells me, hey, R is a rational number. This is your result. So if I take n to be equals to 3, you have a member in B that is not in A. So we found the counter example. So this is not true. Definition of set equality. When do we say two sets are equal to each other? So two sets like A and B are equal. It means that A is the same as B if and only if and only if A is a subset of B, A is a subset of B, and at the same time, B is a subset of A. Why this definition is important for us? Because when we try to prove theorems, lemma, propositions about equality between two sets, we have to follow this definition. We need to show that the first set is a subset of the second set, and the second set is also the subset of the first set. So note for you, this definition is used in proving theorems. When you try to prove a theorem about equality between two sets, and we try to use the very first method that was direct proof, proof by definition, this is the definition that you need to apply. Give us an example. Well, question says, prove these two sets are equal to each other. prove the first set A, which is defined as the set of all integers like m, such that m is 2a, even numbers, even integers, and a is an integer. This guy is equal to the set of all integers like n, such that n is equal to 2b minus 2 for some integers like b. And let us call it set b. Question says, prove these two sets are equal to each other. Prove that A is equal to B. It means that we need to show that A is a subset of B. A is a subset of B. It means that if I take any random element in A, that random element lands in set B. And also, we need to show that B is a subset of A. So, and B is a subset of A. It means that if I take any random element in set B, that random element lands in set A. About this. So here we start. We want to show that A is a subset of B. It means that we need to take a random element in A. But what are the elements in A? The elements in A are M. So we take an element in A like M. And we show that M belongs to B. This is our goal. This is our goal that we have. We take a random element in A and we show that that element lands in B. Okay, any element in A has form 2 times A. M can be written as 2A. Okay, perfect. My goal is to show that it can be written as 2B minus 2. Well, okay. So if I define A to be B minus 1, then I'm done. Let A be equals to B minus 1. By direct substitution, M is equal to 2 times B minus 1, or 2B minus 2, which is in set B. So we're done. Let's put a smiley face, and I'm done with the whole proof. So our goal is to show that we take an element in B, and we show that it belongs to A. This is our goal. So let us take a random element in B and N. So N, which is written as 2B minus 2, belongs to B. Well, we say that, well, okay, if I factor out 2 here, N can be written as 2 times B minus 1. B minus 1 is just an integer. I can call it A. So I have 2 times A, which belongs to A. Another smiley face. So we just proved that A is a subset of B, B is a subset of A. So it means that A and B are two exactly equal sets. Okay, very well. We have sets, we have subsets, then we talked about equality between sets. Now, how to make it more interesting? How do we actually build new sets? What are the operations between sets? Well, here you have tables of data or sets in structured query language. Your job is to combine those tables in the programming language that you're using or combining your sets using operations. This is our goal. Our goal is to build new sets. On page 4, our goal is to build new sets. Okay, perfect. So first of all, we're going to talk about some operations between sets, and then we're going to talk about power set. Operations between sets. Very well. Like logic, remember we had a statement like P, and we find the negation of that statement with not P. This is what we learned in logic. I'm going to write down the logical definition, logical equivalence of all of these operations that we're going to use. In logic, we had P and not P. When it comes to the language of sets, we have set A, and we have its complement, A complement. Well, okay, but how do we write down the mathematical format of this set? We don't know what elements are included in that set. Before writing down the official definition here of the A complement or the complement of a set, we're going to talk about the largest set possible that we call it universal set. Note that. We need the largest set. That set includes everything that we know and we don't know. The largest set that we call the universal set. Universal set. Think about the universe, including all planets, all stars, all galaxies, the universal set. We denote it by U. We denote it by U, and we call it the universal set. Why are we defining the universal set? Because we need to have something, some framework with boundaries when we are talking about some sets like the complement of that set. When we graph sets, the universal set is usually denoted by a rectangular shape. We say that this rectangular set is the universal set. We have set A. We define the complement of set A to be the set of all elements such that that element is not in set A. Logically, a complement is equivalent to not P. So set language, operations between sets, and the logic equivalence. We have set A, its complement, denoted by A, and a little C on top of it. Note that different books might give you different notation. For example, in other books, a complement is denoted by a bar or a prime. Again, the meaning is just a complement, which is the set of all elements like X belongs to the universal set in the universal set such that that element is not in set A. This is the very first operation that we are using. Complement or equivalent to that, negation. If we have two sets, like A and B, we can take the intersection between these two sets. The intersection is the set of all elements like X such that X belongs to A and X belongs to B. X is in A and X is in B. Logical equivalent, P and Q. This is the intersection. We have the union, A union B. This is for union. Is the set of all elements like X such that that element is either in the first set or it might not be in the first set, it might be in the second set. X belongs to A or X belongs to set B. The logical equivalence is P or Q. And finally, we define the difference between two sets. A minus B, the difference between two sets, is the set of all elements that are in the first set, not in the second set. So this is the set of all elements like X such that X is in A and X is not in set B. So equivalently, you have P and not Q. If you want to write it down, you get P and not Q. Well, can we visualize these? Of course, why not? For the first one, the complement of the set complement. For the complement of the set, you have the following. Remember that when you're working with the complement of the set, you definitely need to identify your universal set. So this is your universal set, whatever it is. It might be R, it might be complex numbers, that depends. Set A is here. This is your set A. Well, here we have everything that is in U, but not in A. It means that we have to shape outside set A. This is a complement. Everything that is not included in set A or outside set A complement. What about the intersection between two sets? Suppose you have set A and you have set B. The intersection between them or all the common elements is going to be located here in the shaded area. So this is A intersection B. What if we are talking about the union between two sets? Well, when we are talking about the union between two sets, we need to have our universal set. Universal set can be there, it cannot be there, that's absolutely fine. Let's just use these two symbols. Suppose you have two set A and set B. The union between them, read this carefully. It says all the elements like X such that that element is in the first set or in the second set. So we shade all elements in set A, their intersection, all elements in set B. This is A union B. Finally, A minus B. We have two sets, A and B. The definition says, well, it is the set of all elements that are in the first set, not in the second set. So it means that we have to exclude the second set. We have to exclude this. It means that we shade only this part. So this is A minus B. Well, can we have sets with no intersection between them? Or let me ask you this. What is the intersection between rationals and irrationals? Question. What is the intersection between rationals and irrationals? What is the common elements between these two sets? Or can we have sets with no intersection? The intersection between rationals and irrationals is nothing. It has nothing in that set. So remember that. When we define intersection, union, or anything else, we're using curly brackets. Curly brackets. The outcome must be a set. The intersection between the rationals and irrationals is a set with nothing in it. What's the name for it? The name is empty set. There is no intersection between Q and Q complement. We say that these two sets are disjoint from each other. We call these disjoint set. A intersection with B is empty, empty, it means that there is no intersection between A and B. There is no intersection between them. Awesome.